My name is Manish. I work at Merit, and I'll be talking very quickly about the ugly five-letter word that I surprisingly haven't heard mentioned very much in the past couple of days, namely CALEA. So what I'm going to talk about is our experiences in going down this path because we're required to go down the path as per the FCC regulations. So a couple of months ago, we at Merit decided to look at what would it take for us to do what is required for the CALEA to perform the wiretaps. We took a look at the standards and we said, well, rather than going down the vendor path, what if we tried to just implement what the standard says and try to be as close to the spirit of what is required to get there. So what I'm going to describe is a couple of experiments that we did to see whether we could actually do this, whether this was feasible, and some quick cost trade-offs. What would it cost us to implement our solutions versus going out to the vendor path? So our goals were mainly develop an experimental reference architecture that would serve as a model for CALEA compliance, determine what level of compliance is possible at a reasonable price point, because the standard doesn't really specify various performance criteria. What percentage of packets are you expected to tap? Are you expected to tap 100%, 99% of the time, or 100%, 100% of the time? It's an extremely vague standard. It's still not even a standard. It's just a proposed standard, so we don't even know how it's going to evolve, even though the deadline for filing paperwork is next week, I believe. So we decided to basically dig in and see what's going on and how we could approach this problem. Of course, one of the key things we wanted to keep in track of was use simple hardware, COTS where possible, because cost is a key factor, given that we have, well, at least at Merit, about 9 or 10 different points where we think we would need to apply this. Of course, we would need to look at 10 gig solutions, because those links would be 10 gig. And more importantly, one of the key goals was our approach in this was the NANOG approach, which is let's build open source tools that others can use to and contribute to. We believe that if we go down this path on our own and we're the only ones using our tools, it may not align with the standard, it may not even be useful. But if there's enough community support for this, it can become a well-accepted practice for doing this. So, 2 experiments that I'm going to describe very quickly. The first was just a very, very preliminary experiment. Use a Dell workstation with 2 gig interfaces and see what we can tap. And then the second experiment was a much more realistic experiment where we decided to say, well, let's try to scale it up and see what happens at 10 gig and what performance we get. We're using open source tools. These are Linux-based tap boxes. The second experiment uses a 10 gig card. We're running Linux on them. We're using iPerf as a traffic generator for the first part, and then the second, and of course there's live traffic in the background. So our experiments were conducted in a live network. Our metrics are that we're trying to track is using simple hardware, simple software, what kind of captures can we perform, and what did our platform cost. So the first experiment was simple. We installed a capture desktop workstation in our building switch. Just use simple port mirroring, and then try to measure if somebody's coming in off of a DSL line across the internet, and you try to do a tap at the building level, what kind of performance would you get? The aggregate bandwidth that was going on, the switch at the time was about 200 megabits per second in the first test, and then about 400 megabits per second in the second round. And we do measurements for simple and large UDP flows. And here are results. So for what you can see is roughly across the board, we see less than 1% packet loss. And more importantly, the packet losses that we were seeing were going across the internet anyways. They weren't as a result of the tap box itself. So second experiment was the scale-up experiment. We ran it off of a 10 gig span port across a fiber link. And what we're doing over here is going across from the Merit offices to a iPerf sync, sending traffic all the way across from Ann Arbor to Chicago. We do a span port on the 10 gig port, and that's where the tap device is installed out in Chicago. And of course, for this experiment, we have implemented the so-called law enforcement agency collector. So the tap device is not only capturing the traffic, it's doing the encapsulations, and it's sending the collected data back to the collector. the aggregate bandwidth, the aggregate background traffic that we have on the switch at that time is anywhere between 2 to 2.5 gigabits per second. And within that 2 to 2.5 gigabits per second of aggregate traffic, what we're trying to do is actually capture the small stream of traffic that is user generated by our iPerf testing. Of course, we had to keep in mind additional complications such as multiple VLANs, how do we tap across all VLANs, MTUs in the retransmission path, and so on. So very quickly, our results. The 10 gig cards, because the platform is a little bit better, it's a little bit nicer Dell server, it's using the PCI Express bus, we do get better capture performance. We're seeing less than 1% packet loss on our captures for varying amounts of traffic and at varying stream bit rates. This is, so what this graph is basically showing is the stream bit rate, the test stream bit rate that was pulled out of a 2 to 2.5 gigabits per second of background traffic. And of course, we do the measurements at both points, which is both measure how much packet you were capturing at the tap and how much packets were actually received by the actual collector, because you do have to capture it and then retransmit it back out. Conclusions very quickly. Return path characteristics were an important factor in this, because on the return path to the law enforcement, you need to do some encapsulation, some custom headers, and if you're not careful, you will run into MTU problems very quickly. So that's one thing you need to watch out for. It seems that captures at 2 to 2.5 gigabits per second of aggregate bandwidth seems to be feasible. The hardware cost for this platform was about $2,500, of which the server cost $1,300 and the 10 gig cards is about half of the cost. So the tool set that we're developing has 2 or 3 different parts. The first is the TAP program itself, which is using PCAP library to do the packet captures on the right filters. And then it will also, after doing the capture, will do the encapsulation and the retransmission back out. There's the example receiver tool, which will receive the packets, unencapsulate, and generate back out a PCAP file. And then, of course, there's some additional stuff that you need to do in case you have multiple tap points. You need to be able to tap at the same time and have some sort of a controller tool set over this as well. So essentially what I'm describing today is a practical approach that we took in trying to figure out how we were going to do CALIA conformance using custom standard hardware, open source, freely available Linux-based software, and also trying to push our what we've done and what our experiments are to the rest of the community. And soon, hopefully, we'll have a website up with which is going to be open, which is going to host the open source tools that we've developed so far, and the community is welcome to participate and help make them better.
And are there any questions? We've got about just under 2 minutes to take questions. And while we're taking questions, can Dave Knight come up here and get ready?
Hi, Hi, Jared Mach, NTT America. I was wondering if your tools support the T1 IAS protocol, which is the only current safe harbor standard for any sort of internet type intercept that is recognized within under the Act.
Right. So what we were looking at was the PTSC proposed standard, which proposes 3 different encapsulation mechanisms for transmitting the captured packets across. We're implementing, I believe, the IAS packet format, and we're implementing the packet format which is described in the proposed standard. So we believe we're as close as can be to a draft. If the draft were to change, we'd have to make changes as well. But yes, I do believe we are complying with the standard laid out in the PTSC proposed standard.
Okay. Also, have you worked with the CALIA implementation unit at DOJ to let them know of the availability of your tool set and whether or not they see that would fit, the needs of their requirements?
So the answer to that is no, we have not yet looked at them. This project is only about 2 months old, and we wanted to do very quick feasibility tests first before we had any reasonable level of confidence in what we were doing and whether it would actually work.
You have 30 seconds.
Okay, really quickly. Sorry, I'm Chris. I work for Verizon Business. So your approach is essentially to tap close to the end user that you need to do, and with a physical tap, yes?
We're tapping off of a 10 gig switch, so it's actually towards the middle of the network. It's not close to the campuses. We are trying to be what we call gateway compliant. So we are not tapping on our customer interfaces, but actually on our outgoing internet interfaces.
And Ethernet only, not like channelized interfaces or SONET interfaces?
So far, the hardware card we've been using is only the 10 gig Maricom adapter, so only Ethernet. That's right.
Okay.
Okay, thanks. Thanks, Manish. That was great. Cheers.